In this video, I want to talk about formal charge. I'll go over what it is, how it works, and what we can use it for. First, we need to know what a formal charge is. A formal charge is a hypothetical charge on an atom, in a molecule, or a polyatomic ion. A formal charge must not be confused with the charge of a molecule, a charge due to the surplus or the lack thereof electrons in the molecule. We looked at molecules with charges and drew them with brackets around the molecule with the charge on the upper right-hand corner. The charges on the molecule gave no indication where the charge was in the molecule. A formal charge gives us a more specific location of the charge, revealing which atom holds the charge within the brackets of the molecule. A formal charge can be abbreviated by Fc or denoted as Q star. The formal charge is represented by a charged value with a circle around it, and placed by the atom it represents within the molecule. So this charge represents the entire molecule, and this charge represents a hypothetical charge on the nitrogen atom. How does it work? When we use a strategy to draw Lewis structures, once we determine the number of valence electrons in the molecule, there is really no way to keep track of them after we determine how many there are. Then we arbitrarily go back and assign these valence electrons to atoms as if we know where they came from. A formal charge gives us better bookkeeping skills to keep track of the valence electrons in the molecule, so there is less ambiguity. This is done by using a more detailed and accountable method to make sure charges in the atom make sense. With this extra set of guidelines to follow, we can make sure the valence electrons are distributed accurately and correctly throughout the molecule. This added insight gives us more confidence the structure is correct. A formal charge is a hypothetical charge on an atom in a molecule or polyatomic ion. This is hypothetical because it assumes bonding electrons are shared equally between the atoms involved, which is an idealized situation. In reality, electrons are usually not shared equally. A formal charge does not consider polarization or polar covalent bonds that are brought about by electronegativity. This over-exaggerates the covalent character of bonds equally sharing electrons. So why is the formal charge so important and what do we use it for? We kind of went over this when we described how the formal charge worked. To get straight to the point of what a formal charge is used for, a formal charge can help us determine the correct distribution of electrons throughout the molecule and write a correct Lewis structure in most cases. We won't get into it in this video, but a formal charge can also help to write the correct resonance structure, which is a very important concept in chemistry. In a previous video, we were drawing a Lewis structure for carbon dioxide, and we came up to a point where we were going to distribute the electrons so we could get carbon to have a filled outer shell of 8 valence electrons. And the first step, we took the lone pairs on the oxygen on the right and distributed those out to a bond between the oxygen and the carbon. And we got to this point right here. And at this point, we could have either went to the oxygen on the left and distributed those out to a bond between the oxygen and the carbon, or we could have went to the oxygen on the right and distributed a lone pair of electrons to an additional bond between the carbon and the oxygen, which would give it a triple bond. And there's nothing that would indicate which molecule would be correct from the rules given to us on how to draw a correct Lewis structure. Both of these molecules would pass the verification test. They both have the same amount of electrons as they would have had in step 1. And all the atoms in the molecule would have a filled outer shell of 8 valence electrons. So in situations like this, a formal charge can be applied, and it'll become very clear on which one is the correct Lewis structure. When we calculate the formal charge, we need to find out 2 types of valence electrons: the valence electrons in a free atom, and the valence electrons assigned in the Lewis structure. Once we determine those valence electrons, we subtract the valence electrons from the Lewis structure from the valence electrons in the free atom. Valence electrons of a free atom simply means it's an uncombined atom. It's not bonded to anything else. And we find the valence electrons the same way we do when we write a Lewis structure. We just pull up a periodic table and find what group the atom falls in, and that will give us the valence electrons of that atom or a free atom. So if we had carbon, it would be in group 4A, so it would have 4 valence electrons. Nitrogen would be in 5A, so it would have 5 valence electrons. Oxygen would be in 6A, so it would have 6 valence electrons, and so on. So the valence electrons of a free atom simply means the atom by itself that is not combined with another atom. We can find that by pulling up a periodic table and seeing what group it's in. The other type of valence electrons we need to know are the valence electrons that are assigned to the atom in the Lewis structure. There are two categories of valence electrons in Lewis structure: lone pair electrons and bond pair electrons. The lone pair of electrons are lone pairs of electrons belonging entirely to the atom that they're attached to, and the bond pair of electrons are electrons in the bond, and they're divided equally between the bonded atoms. When we count up the valence electrons assigned in the Lewis structure, this is equal to the number of lone pair of electrons plus half of the bond pair electrons. So mathematically, we could write it out like this. Let's go ahead and start adding up some valence electrons that are assigned to atoms in this molecule. So let's start with oxygen. And starting out with a lone pair of electrons, we can see there's two lone pair of electrons, so that would give us a total of 4 valence electrons. There are 2 bonds that are bonded to oxygen, and each bond has 2 valence electrons in it, so that would give us a total of 4 valence electrons. And here we say that we get half of the bond pair electrons. We divide that by 2, and that would give us 2, so we can put 2 right here for half of the bond pair electrons, which would give us a total of 6 when we add them together. So for oxygen, there would be 6 valence electrons assigned to oxygen. Let's look at carbon. Carbon has 4 bonds, and each bond has 2 valence electrons in it, so that would be 8 valence electrons, and we would only get half of those. So that would give us 4 valence electrons. There are no lone pair electrons, so carbon would have 4 valence electrons. Looking at hydrogen, it has no lone pair electrons, and it has 1 bond, and each bond has 2 valence electrons, and we divide that by 2, which would give us 1, so each hydrogen has 1 valence electron. We know what valence electrons are in a free atom, and we know how to get them. And we know what valence electrons are that are assigned to a Lewis structure, and we know how to get them. We know how to calculate the formal charge, which is done by subtracting the valence electrons on the Lewis structure from the valence electrons of a free atom. We use these abbreviations to describe what each valence electron was, and if we plug those into the formula right here, we can get this final formula, which would describe how to get the formal charge. So we take this description and simply plug it into this part of the formula, and we take this description and plug it into this part of the formula, and we arrive at a formula that looks like this, which just describes the formula in more detail. We abbreviated the valence electrons in a free atom. To be more descriptive, we have the number of valence electrons in a free atom. So with the 2 types of valence electrons, one from the free atom and then one that's on the Lewis structure, if we distribute out this negative sign and take away the parentheses, we have a more simplified formula, so we can just plug the values in and subtract. And subtraction is a little less cumbersome than this formula right here. So with our final equation, we can go ahead and evaluate a molecule. The order of the equation is we have the number of valence electrons in a free atom minus the number of lone pair of electrons minus half of the bond pair electrons. First up is hydrogen, the number of valence electrons in a free atom. We can find that on the periodic table. Hydrogen's in the first column. We know it has 1 valence electron. And looking at the molecule, we know that it has 0 lone pairs, and it has one bond, so each bond has 2 valence electrons, and we get half of that, so we would have 1 bond. So 1 minus 0 minus 1 give us 0. And looking at the other hydrogen, which is the same, so we would have the same formal charge with the other hydrogen. Looking at carbon, the number of valence electrons in a free atom would be 4. Carbon is in the 4th group on the periodic table. Looking at the molecule, we can see that carbon has no lone pairs, so we have 0 for that. And it has 4 bonds, and each bond has 2 valence electrons. So 4 times 2 is 8, and we get half of the bonding electrons, so that would give us 4. So 4 minus 0 minus 4 would give us 0. Next up is oxygen. We can find the valence electrons of a free atom by going to the periodic table, and oxygen is in group 6, so it has 6 valence electrons. And looking at the molecule, it has 2 lone pairs, and each lone pair has 2 valence electrons, so that would be a total of 4 valence electrons. Oxygen has 2 bonds, and there are 2 electrons in each bond, so that would be a total of 4 valence electrons for the bonding electrons. And we get half of those, so that would give us 2 valence electrons for the bonding electrons. So we have 6 minus 4 minus 2 would leave us a formal charge of 0. So this is a neutral molecule, and everything checks out because there's no charge or brackets around the molecule. Here are some guidelines to follow when we're writing a formal charge on a Lewis structure. Number 1, the sum of the formal charge in a Lewis structure must equal 0 in a neutral molecule and must equal the magnitude of the charge in a polyatomic ion. Number 2, when formal charges are required, they should be as small as possible. Number 3, negative formal charges usually appear on the most electronegative atoms, and positive formal charges on the least electronegative atoms. Number 4, structures having formal charges of the same sign on adjacent atoms are unlikely. Let's go ahead and review the molecule that we just evaluated with these guidelines. We determined that there is a formal charge of 0 on every atom, and if there's a formal charge of 0, we don't put anything on the atom. Looking at the first guideline, it says the sum of the formal charge in the Lewis structure must be 0 for a neutral molecule and must equal the magnitude of the charge in polyatomic ions. So this checks out. All the formal charges are 0, and it's a neutral molecule. The next 3 rules really don't apply. Where formal charges are required, they should be as small as possible, and they didn't have formal charges. The third rule says that negative formal charges usually appear on the most electronegative atom, and positive formal charges usually appear on the least electronegative atom, so this doesn't apply. And the last one says structures having formal charges of the same sign on adjacent atoms are unlikely. Doesn't apply. So with the rules that do apply, they check out. Previously, we used this slide as an example of how a formal charge could help us decide the correct Lewis structure. So I want to take both of these molecules, this molecule and this molecule, and put formal charges on them and see what we got to help us determine what the correct molecule is. We have an oxygen, 3 sets of lone pair electrons, and 1 bond. Next up is the carbon, and we have 4 bonds on the carbon. In the last oxygen, we have 3 bonds and a set of lone pair electrons. So starting off, we can determine the number of valence electrons in the free atom, and we can do that by going to periodic table. Oxygen is in group 6, so it would have 6 valence electrons. It has 3 sets of lone pair of electrons, and there's 2 valence electrons in each lone pair of electrons, so that would be 6 valence electrons. It has 1 bond, and there's 2 valence electrons in 1 bond, and half of that would be 1, so we have 1. So 6 minus 1 is negative 1. So for this oxygen, we can put a negative formal charge on it. We put a negative sign with a circle around it. For the next atom, we have carbon. So the number of valence electrons in the free atom can be found on the periodic table. And it's in group 4, so the free atom has 4 valence electrons. Next, we have the number of lone pair electrons, and it has no lone pair electrons. And it has 4 bonds, and each bond has 2 valence electrons, so that would be a total of 8 valence electrons. And we take half of those, so that would leave us with 4 valence electrons. And 4 minus 0 minus 4 equals 0, so we don't have to put anything on the carbon atom. In the last oxygen, we can find the valence electrons, the number of valence electrons in the free atom by going to the periodic table. Oxygen's in group 6, so it has 6 valence electrons. It has 1 set of lone pair of electrons, so it has 2 valence electrons for that. And it has 3 bonds. Each bond has 2 valence electrons, so that would be a total of 6 valence electrons. And we take half of those for the oxygen, so that would be 3 valence electrons. So 6 minus 2 minus 3 equals positive 1. And we can put this formal charge on this atom by putting the sign on it with a circle around it. If it's 1, then we can just put the sign on there. If it was more than 1, we would put magnitude of the charge with a circle around it in the sign. Okay, let's go ahead and review this molecule with these 4 guidelines. We said there is a negative formal charge on this oxygen. The carbon was neutral, and there was a positive charge on this oxygen. So looking at the first rule, the sum of the formal charge in the Lewis structure must equal 0 for a neutral molecule. And this is a neutral molecule, so this checks out. For the second guideline where it says where formal charges are required, they should be as small as possible. For this guideline, I want to wait until we have all the structures build up so we can compare them and better determine which one has the lowest formal charge. The negative formal charges usually appear on the most electronegative atoms and positive formal charges on the least electronegative atoms. And the oxygens are the most electronegative, so that checks out for this oxygen. But this oxygen has a positive formal charge, and that doesn't make sense because the carbon would be the least electronegative. So this fails. All right, let's move on to the fourth and last guideline. It says structures having formal charges of the same sign on adjacent atoms are unlikely. So on the left, we have an oxygen that's negative, and on the right, we have an oxygen that's positive. In the center here, where the carbon is, this is a neutral carbon. So this would make it impossible for 2 atoms of the same formal charge to be next to each other. So this checks out. When we review this molecule with a formal charge of -1 on the left oxygen, would check out, but a formal charge on the right oxygen where it has a positive formal charge does not check out. This does not make any sense. The other option we had was a molecule that looked like this. Let's go ahead and put this up on the chart and see what we get. Going left to right, we had an oxygen with 2 sets of lone pair electrons and 2 bonds. Next up, we had carbon with 4 bonds. And the last one, we had an oxygen with 2 sets of lone pair electrons and 2 bonds. I'm going to go through this pretty quick since we already did one previously. So the number of valence electrons in a free atom is in group 6 and has 6 valence electrons. There's 2 sets of lone pair electrons, so there's 2 in each one, so that would give us 4. And there's 2 bonds, and there's 2 valence electrons in each bond, and we get half of those, so that would give us 2. So 6 minus 4 minus 2 would be 0. With carbon, carbon is in the 4th group, which would give us 4 valence electrons for a free atom. There are no lone pair electrons, and there are 4 bond pair electrons, which would give us 8 valence electrons total, and we get half of those, so that would be valence electrons. And 4 minus 0 minus 4 would be 0. And this oxygen is essentially the same as the oxygen on the top row, so I'm going to put 0 there. And we have 0 formal charges on all 3 atoms. We determined that this had a formal charge of 0 and that it was a neutral atom. So looking at step 1, the sum of the formal charge in the Lewis structure must equal 0 in a neutral molecule. The second guideline is where formal charges are required, they should be as small as possible. The third guideline is negative formal charges are usually on the most electronegative atom, and positive formal charges are on the least electronegative atom. Since we don't have any formal charges, this guideline would really not apply. And the last guideline is structures having formal charges of the same sign on adjacent atoms are unlikely, and this doesn't apply because we don't have any formal charges. It's a neutral molecule. So this does not fail any of the tests or guidelines. So this would be the correct Lewis structure for carbon dioxide. I do want to circle around, come back to the first structure we had, and look at the second guideline where it says where formal charges are required, they should be as small as possible. And I wanted to wait until we had both structures so we can compare them, because it's really the only way you can apply the second guideline. It's pretty obvious once you have all the structures lined up next to each other. This structure has a formal charge of 1 on each side, right here and right here. The last structure we had was this structure, and it has no formal charges. So obviously that's the molecule that has the smallest formal charge. In summary, we knew right away the molecule with the formal charges on it would be rejected. This is because there was a positive formal charge on the oxygen with high electronegativity. In addition to the mismatched formal charges, once we compare the two molecules together, it would become obvious that one of the molecules would have no formal charge, and that would be the correct molecule.